Welcome to the first training module for GPI, the Graphical Programming Interface. I'm Nick Zwart, and I'll be guiding you through this exercise. Today we'll be looking at taking cross-sections out of an image, but this is really just a subset of a more common activity in GPI, which is data manipulation. This cross-section network demonstrates a case where we want to take and compare subsets of data. In this case, we're taking the image cross-sections and plotting them. The node configurations in this example are often used in this way for plotting and viewing 2D images. The network exercises are included with the GPI distributions and can be found under the Help menu, then the Documentation button. This opens a file browser window containing GPI documentation, training material, and the examples. Double-click the examples folder and drag the cross-sections network into the GPI canvas. It should look something like this. The key concept for this exercise is to work with the reduce node, specifically making subsets and masked sets. I'll also introduce the reader node, the vector convention that we use in GPI, and the windowing widget in the image display node. So we'll look at reduce. We have a little example network starting with the shapes node, which is generating an array, passing it to reduce, and then passing a subsequent array to statistics. The shapes node is generating an array with dimensions of 100 by 100 by 100, and we can tell by the output dimensionality that reduce is just passing all the data. If we open the reduce menu, we see these same dimensions are reported in the uppermost widget, and that all the dimensions are set to pass. If we set a dimension to slice, this will return a two-dimensional array at the specified index of the input 3D array. And you can see from the canvas edge that there is a 2D array with dimensions of 100 by 100. Reduce can also crop a specified dimension by selecting the CW option, which stands for center width. When center width is chosen, the first slider centers the crop and the second spans the width of the crop. You can see that as the width is changed, the dimensions shown on the canvas change. The BE button stands for begin and end. This is just an alternative way of specifying the crop indices. Reduce has two outputs, one of which we've been using. This one's called out, and the other is called mask, which can be activated in the menu. The mask is the complement of the array subset. It contains all of the array values that are not included in the subset. All of the array locations of the subset are masked to a value of 0. You can see that the mask array is the original dimensionality of the input array. The use of this function will be explored in the exercise. The reader node used in this example reads data from a NumPy formatted file and produces a NumPy numeric array at the output port. The uppermost widget shows file system information, total byte size, which includes header information if any exists, the array dimensions, and the data type. The data in this array represents an image stack with dimensions 24 for number of images, 436 by 436 for the image size, and 2 for real and imaginary complex data. The nodes are usually written to accept a specific type of data. In this case, there's a downstream node that is expecting complex data. However, the real and imaginary data were saved as normal floats in the last dimension of this array. This is noticeable because the last dimension has a length of 2. After the toComplex node, you can see that the last dimension is removed because the data have been converted to the complex type. In GPI, the last dimension of an array is called the vector. This is a convention or shorthand that simplifies the handling of port requirements. The vector element usually comes into play when working with complex data, coordinates for case-based trajectories, or drawing coordinates for GL objects. In this case, the vec to complex option is checked, indicating that the vector should be treated as a complex pair. The output port of the reader node shows that the data elements were read as type float32. Hovering over the toComplex output shows that the data were recast to the complex 64 type. For this example, it's helpful to be able to scale the image shown in the viewport widget of the image display node. This is done with the LWFC widget, which is collapsed by default. When you double-click the widget to open it, you'll see 4 sliders that are for level, window, floor, and ceiling. The ceiling slider caps the max pixel value, and the floor raises the minimum pixel value. The level and window sliders are alternatives that accomplish the same thing. Now that we've gone over the concepts for this exercise, take some time to explore the network and complete the task. You'll notice that the image cross-sections are taken horizontally, so your task is to make them vertical and add a 4th cross-section. So now go ahead and pause the screencast. And we're back, so let's look at the solution. As a recap, this network loads a multi-slice image stack as a numeric array from a file, converts it to a complex data type, slices off a single image from the stack, and then passes to the RIMP node. RIMP stands for Real, Imaginary, Magnitude, and Phase. In this case, the complex data is converted to magnitude data. The statistics node is just thrown in for perusing. The reduce node is taking cross-sections from the image data and masking those sections out so their location can be seen in the viewer. The cross-sections are then sent to the plotter for comparison. We see that the dimension 2 slider is set to slice at various Y locations in the image. So to make these slices vertical, we first turn off the compute to prevent downstream execution. Then change the widgets to slice the first dimension and pass the second dimension. When we turn on compute, the cross-section is vertical. We can quickly modify the others by pausing the canvas and changing the settings for the other 2. The sliders can then be adjusted so that the cross-sections don't overlap. By inspecting the ports, we see that the cross-sections are 1D and are sent to the plotter, and the mask is 2D and is connected to downstream reduces. To add a 4th, we first copy and paste a reduce, then connect it in the same fashion as the previous 3. The mask port is connected to the image display, and the out port is connected to the plotter. And this is the 4th cross-section. This example has given you an introduction and some hands-on experience with some of the basic GPI nodes in a commonly used configuration. You can find more information by visiting gpilab.com.